thermodynamics. This one's going to be a bit short because the first sort of half of thermodynamics is still included on the test. Everything that has to do with enthalpy, calorimetry, heat changes. But the second half, that included entropy and Gibbs free energy and spontaneity, is not included. So there are several slides that are included in this presentation in Google Classroom, but I won't be talking about today because they are not included on the AP test. You can still take a look at them if you want, though. So the whole idea behind thermodynamics is that we can use it to describe the role of energy in reactions and predict whether or not a change is going to occur. So the concepts in this idea, we've got conservation of energy. We know that energy is not created or destroyed, that it can be used as heat or work, that energy is transferred from high energy or warm regions to low energy or cold regions. We talked about specific heat and calorimetry, applications of Hess's law, and the ability to use energy to perform work. Now these last 3 points are the ones that we won't be talking about today because these are no longer included in the test curriculum. So remember our laws of thermodynamics. First one was conservation of energy. We can't create or destroy energy in a process. It's constant. The second law was that the total entropy of the universe increases for any spontaneous process. The third law, the entropy of a pure crystalline substance at absolute zero is zero. So really, since entropy is no longer part of our curriculum, you just need to worry about the first law. Energy is not created nor destroyed. The biggest equation in thermochemistry and thermodynamics is the MCAT equation. Q equals mc delta T. This lets us see the heat change that occurs in a process. So our Q is our heat lost or gained, M is the mass of the substance, C is its specific heat capacity, and delta T is the change in temperature, T final minus T initial. A quick reminder, sorry about the fuzzy image here, but it demonstrates the point well. This is a heating curve of water. A quick reminder that if you're taking water from -20 to 120 degrees Celsius, you can't do that calculation in one step because you're going through phase changes. So anytime the temperature is increasing, you can use the MCAT equation. Q equals the mass of your water, the heat capacity of your water, times your delta T. In here where we've got these two phase changes, melting and vaporization, we don't have a change in temperature because remember at phase changes, temperature is constant. Your heat here is your mass times the enthalpy of fusion for melting or the enthalpy of vaporization for vaporizing. So you would actually have to do this process in 5 steps here. Additionally, technically the heat capacity is going to be different for ice, liquid, and vapor water. Mostly we'll use the MCAT equation when doing calorimetry experiments. Remember the whole idea behind this was that we could calculate the heat change of the system by measuring the heat change of the surroundings. So we perform a reaction surrounded by water. We measure the water's temperature change. We use Q equals mc delta T with the mass of the water, heat capacity of water, and temperature of the water. That tells us the heat either absorbed or lost by the surroundings, which must be equal and opposite to the heat either lost or absorbed by the system. The enthalpy of reaction is expressed as delta H. You can also calculate this. You can use MCAT if you've got the information for it. You can also, if you've got a chemical reaction, use the tabulated data in the back of your book by taking the energy of the products minus the energy of the reactants. So if you've got a chemical equation This delta H, this means the standard, because of the degree sign, the standard enthalpy of formation of products and reactants. And there's tables of these values in the back of your book if you remember. So if you've got a chemical equation, these numbers here, N and M, would be the coefficient in front of each substance. So if you had, for example, if one of your products was 2 moles of water, then the energy of your products would be 2 moles times the standard heat of formation of water. Alright, and you can solve for the total delta H of the whole reaction with this equation. A quick reminder, the standard enthalpy of formation of pure substances in their standard form is 0. So for example, O2 gas, oxygen gas at room temperature, has a standard heat of formation of 0 because it naturally exists like that in the gas form. You don't have to put any energy into making it exist like that. That's what it was already doing.